Oh, not sure there's people here. Okay. Okay, it's time to start. So, any question from this time? Yeah, so we have a few people in classroom now. Okay, anyway. So yeah, this time we have the introduction about what are signal and systems. So, a very brief review. Signals are functions, and systems are functions that make the function, maybe a signal to another signal. Okay, and today we'll focus on signals. So signals are functions of some independent variable, and we'll mostly focus on signals with one independent variable, and we'll call that independent variable time. So here we can have continuous time signal and discrete time signal like this. And well, for discrete time signal, the discrete time steps are always integer. They all have the distance between them by 1. That's our convention in this course. Hello. Wait, why is this be weird? Hello. Yeah. And anyway, so from the from the circuit system example, we see that we can have and from the circuit system example, we see that we can define, well, circuit system will have energy and power. So power of a circuit system, we see that is proportional to voltage square or current square. So current and voltage can be seen as a signal in this circuit system. And so we try to abstract this intuition in circuit system and define energy power for arbitrary signal. So for arbitrary signal, we just define the power as the signal absolute value square. And from here, you can define energy. So you integrate the power through some time. That's the total energy spent. And then you can go backward to calculate average power. So you divide by the total time spent. And so the energy divided by time becomes the average power, etc. Okay. And then the average, you can also take the average period to infinite. So you have or the summation period to infinite, so you have the total energy over infinite time and the average power over infinite time. And because you are dividing and multiplying infinity, so when the total energy is finite, the total power will be 0, and when average power is finite, the total energy will be infinite. Okay, so that's a quick review of this time. Any question? If not, then let's go to the transformation of independent variable. Okay, and yeah, this will be the first class. Okay, so we have a lot of transformation. So basically, we do transformation on independent variables. So basically, we do transformation on time. Okay, so the first 3 are transformation, and the last 2 are kind of related concept. Okay, so are concepts that are derived from the transformation. So let's first see what the transformation. So what do we mean by transformation of signal? It means that we can change the independent variable a little bit, and we will get a signal that's very related. So for example, we have x of n or x of n or x of t here. And the first transformation we do is time shift. So we shift the time variable here, so this n or t by some constant. And so for example, we can have x of t, and we have another signal that's x of t minus t0. Okay? Or we have x of n minus n0. Then you see that we get a signal that looks very like the original signal, but is shifted level right. Okay? And here we have a 2 different example. So we see that, okay, so you can check the calculation. I guess we can check the calculation. But we see that when n is a shift number here, so this n0 or t0, when it's bigger than 0, then your signal is shifted rightward. And that means the signal is delayed. So that's because this is So the picture is what the signal look like at some time step. So you see that, for example, what happened at time 0 is now what happened at time n0. So the signal is happening later, so the signal is delayed. Okay. And yeah, you can check it out the math checkout. So at 0 you will have this x over 0, and now instead at n0 you will have this x over n0 minus n0, which is x over 0. Okay. So here with n0 equal to 8, like this. So the whole signal will get delayed by 8 steps. And similarly on the other direction, if this shift, so the t0 here is less than 0, so actually you have t plus 5 here, then the whole signal is is shifted leftward and is advanced by by this t0 time. Okay, so here you see that this t0 is 5, so at the time, so t0 is actually negative. So at this negative 5 time, yeah, it is negative 5 time, you have x over 0, which is this peak here. Okay, so this is the time shift. You can delay or advance your signal, and so you have usually you write as n or t minus something, and this something is positive, then your signal shift to right. This something is negative, then you shift to left. Okay, question. So that's time shift. And then we also have time reversal. So we're doing linear transformation on this time. Okay, so you can add or subtract by a number, and then we can multiply it by a negative sign. And when you multiply it by a negative sign, you also get a signal that looks very close, but you flip the signal left and right. So yeah, it's quite intuitive by picture here. So you have this shape here from left to right, and you count this shape right to left. Okay. So yeah, so your signal is flip around this x equal t equal to 0 or n equal to 0 line. Okay. So it's a continuous one, and it's a bit more clear. So you have this shape. Now you flip left and right and become this shape. So this is what happens when you put a minus sign on your independent variable, okay, or the time variable. And finally, so the last one of our linear transformation on time is time scaling. Now this one is a bit more tricky. So let's first see the continuous time. Okay, so for continuous time, well, there are kind of two different possibilities. You can, well, you multiply your time by some number. So if your number is bigger than 1, then your okay, so you multiply by some real number. Your number is bigger than 1, then your signal will get compressed like this. So you see you have this kind of Y shape, you have this shape, and you see you get compressed toward this middle line, toward this t equal to 0 line. Okay, and let's see this checkout. So maybe this step, maybe this point was t equal to 1, and then you see that at t equal to 0.5, you are already at x of 2 times 0.5 equal to x equal to 1. Okay. So you see that you multiply a bigger number, then everything happens faster, then the signal gets compressed in. And on the other hand, if you multiply by a number that's less than 1, then yeah, then obviously your signal gets stretched out. So what happened at time 1 now need to happen at time 2. Okay. So yeah, you multiply by a bigger than 1 number, signal gets compressed. Multiply by a less than 1 number, signal gets stretched out. Okay. And so that's continuous time. And but here we see the first time why the discrete signal are a bit weird. So for discrete time signal, time scaling is not always possible. That's because we define our discrete time signal as, okay, so let's go back. I guess like this. Remember we define our discrete signal as like always taking the interval between them as 1. Okay. But if you want to just stretch or compress your signal, then the spacing needs to get stretched or compressed also. Okay, but okay, so if you stretch out, but if you stretch by some or compress by some base number, then the simple point may not be integer anymore. Okay, so actually you can only stretch or you can never compress your discrete signal, because if you Yeah. Yeah, I guess yeah, you can never compress your signal because then you need to compress some point to like some here. Wait, sorry, be confused, but oh sorry. So actually you cannot stretch your signal. So you cannot stretch your signal because there will be like a middle part that's undefined. So for example, if you try to define xn over 2, and yeah, and then at n equal to 1 point, it will map to like n equal to 1/2, map to this n equal to 1/2 point, which is x over 1/2, which is an undefined number. But you can compress your signal, and but only when you compress by integer. Okay. Okay. So yeah, this is defined. But yeah, in general, I think later we'll try to do some kind of time scaling. But in general, you don't do too much of time scaling on discrete time signal because it's hard to match the integer intervals on your sample points. Okay. Any question so far? If not, and then let's see the first complicated part of this course. That is, we try to combine different, we try to combine different parts of those three scaling. So we can have time shift, we can have time reversal, and we can have time scaling. And what happens if we do two of them together? I guess two of them in sequence to a signal. Okay, so yeah, so you see that we can, if we can have a signal that's x over minus t plus 1. So we start with signal that's x over t, and we try to see what it is x over minus t plus 1. And so you see that you need a minus sign on t, and you also need a plus 1 here. So to get this signal, we do need to do two step. So we see that we first change t to t plus 1. And so this is a plus 1, and so plus 1 is actually minus 1. So this is the advance of your signal. You shift your signal to left. Okay, so x of t becomes y of t equal to x over t plus 1. So you shift the signal to left by 1. So becomes this thing. Everything shifts by 1 here. And then you see that you want to add a minus sign on t to get back to x of t minus 1. So so you do another change of variable, so you change t to minus t, and we define another function, z of t, that's equal to y of minus t. So y of t is already x of t plus 1. Then you define z of t equal to y of minus t, and y of t look like this, so you put a minus sign on t here, so you see z of t equal to x of minus t plus 1. Okay, so this is exactly what we want. We want some function that equal to x of minus t plus 1. And then that should be like a time reversal on y of t. So you flip left and right on this thing, and so you got this shape. So z of t equal to x of minus t plus 1 look like this, and you will do this kind of question in your homework. Okay, so question so far. Okay, oh, please, question. Huh? So. Oh no, that's the last slide. Okay, so I think the question is answered on the next slide. Okay, so there is a difference between minus t plus 1 and minus t minus 1, and you actually need to be careful here. Okay, yeah, that's a very good question because it is exactly what we are doing on the next slide. Okay, so you need to be careful about the ordering here to make sure you are getting minus t plus 1 or minus t minus 1. Okay. So if you do this in other order, so if you do the time reversal first, okay. So yeah, so this was what we have, and that's the correct one. And so this one is kind of a trip, but it's easy to confuse on this. But let's see what if we do in different order. So if you do time reversal first, and you got the signal, and so your y of t will be x of minus t. Okay. And then if you change t to t plus 1 on this signal, and then you will shift your signal to yeah, you will shift your signal to left more, and you see that this is a different signal. And what this signal is z of t equal to y of t plus 1, because we shift t to t plus 1. And about y of t, look at this. So you need to change this minus t to minus t plus 1. So you see y of t equal to x of minus t. And what you do is, so z of t equal to y of t plus 1. So what you do is you take y of t and change this t to t plus 1. So t to t plus 1 here and t to t plus 1 here. So this is x of minus t should go to x of minus t plus 1. And so this is actually x of minus t minus 1. Okay. And yeah, so this is a good question, but this is not the correct calculation. Okay. And I think we have a hint here. So you need to remember that. So if you want to figure out what ordering is correct, you remember that what you're operating on is t. So you are either, so what we are doing is we add a plus 1, we add a plus 1 to t, then we add a minus sign to t. All these operations are operating on t. It's not operating on everything inside the parentheses. Okay? So we are changing, yeah, we are adding things to t. That's how I remember things. Okay. And yeah, I guess we can check. We can check a little bit about this is the correct answer. So x of t. So this point is x of 1, and so if so this point with t equal to 0 is also x of 1. So you see this x of 1 mapped to this x of 1, and that's kind of correct. But this one, then you see that x of 1 is at t equal to minus 2, but that's not here. So you put t equal to minus 2 here, it should be x over 3. So you see that this is not correct. Okay. Any question on the change of on sequential transformation on this time variable? Yeah. The ordering is a bit confusing, and you need to get used to. So I think if you are getting confused, it's nice to write this intermediate function here. So you see here we define this y of t as x of t plus 1. Then we define z of t as another function of y of t. Define z of t as y of minus t. Then you can subtract this y of minus t. So you can subtract the minus t inside here. So minus t become minus t, and the minus t become minus t. So you see this is x of minus t plus 1. Okay. So remember, we are changing a variable. So you are changing t to minus t, so this is t to minus t. Okay. So yeah, we are operating on t. Okay. And so this is a combination of time shift and time reversal. Then obviously you can do another combination. So here we have another combination. That's combination of the stretching compressing is time scaling. So we have another combination that's time scaling with time shift. Okay. So yeah, so we have x of 3 over 2t plus 1. And as you will probably guess, so we are operating on t, so we want to get this plus 1 first. So we first shift to t plus 1, and we have y of t equal to x of t plus 1. Then we do another operation on t. Okay, well, we need to see a picture first. So y of t equal to x of t plus 1, and because you are plus a number, means minus a negative number. So the shift you have is negative. So you go to the previous time. So your signal gets shifted to the left, and then you do this time compression. So you multiply t by 3 over 2, then you have z of t equal to y of 3 over 2t, and so you see that this will get what we want. So because t becomes 3 over 2t, yeah, t becomes 3 over 2t, and your final signal is x of 3 over 2t plus 1. So because 3 over 2 is bigger than 1, then everything got compressed by a factor of 3 over 2. Okay? So this 1 becomes 2 over 3. This minus 1 becomes minus 2 over 3. And you can probably guess we'll talk about this similar thing. So you also need to be careful here. So it's plus 1 and then multiplied by 3/2. You need to be careful about the ordering. If you do different order, then you also get a different result. Okay. So if you get 3/2 first, then you compress the signal by 3/2. So this 1 go to 2/3, and this 2 become 4/3. Then you shift by plus 1. Then your signal gets shifted by left by plus 1. Then you see this is a different signal because it is point at the 2/3 will become point at the minus 1/3. We see that this inflection point should actually happen at t equals 0. Okay. And then we can also check the equation. So if you y of t is already x of 3/2t, then 0t equals to y of t plus 1, then what you do is you subtract this t plus 1, and this t to t plus 1, and this t to t plus 1, then you actually have 3/2t times plus 3/2. Then you are shifting too much here. Okay. And yeah, this is what you will do in homework. Any question so far? No? Yeah. Yeah, so this is a big part of homework you will do in chapter 1. And then we can have a general expression. So as we say, what we are doing here is we do a linear transformation on the independent variable t. So in general, what we are doing is we change x of t to x of at plus b. So this is our linear expression about t. So a and b are constant. And we can get some general idea on this. So we see that if a is less than, the absolute value is a is less than 1, then the signal will get stretched, and if it's bigger than 1, it will get compressed. This is just from the time scaling. And then if a is less than 0, you get time reversal, and if a is bigger than 0, you don't get time reversal. The time reversal, like I guess no example here. And also if b equal to bigger than 0, you get advanced time shift, and b less than 0, you get delay time shift. So this is shift to left, and this is shift to right. Okay. Any question? Okay. Yeah. So yeah, this is some kind of summary of these 3 kind of linear transformation. So you can multiply your time by some constant, and you will get stretch or compress, and plus another constant, you get advance or delayed, and you have a negative sign here, you get time reversal. So those are the 3 3 operations you do on the independent variable. Okay. If there is no question, then let's go to another concept. So this is basically the biggest. It's actually the biggest concept of this whole class. We'll spend a lot of time analyzing periodic signal. But first, let's get the idea of periodic signal. What is a periodic signal? Is a signal that keeps repeating itself. So for
Can you please go to the back?
Oh yeah, sure.
The thing is, like, for the 2 last points, the books they say that when it is.
Oh, it's a little confusing because we have a plus sign here, so it's a negative b. Yeah, yeah, it's a bit confusing. Maybe I should change that. Yeah. So yeah, so this is a bit confusing because we have different notations. So it's minus b. Okay. Any other question? Yeah. Okay, then no question. Then let's go to our favorite periodic signal. We'll see this over the whole semester. Okay, and but what's a periodic signal? Is a signal that keeps repeating itself. Okay, so here are very nice illustrations. So we see this continuous periodic signal is just repeating this shape over and over again, and yeah, it's the same shape with the same spacing. It just keep happening. Okay, so this is kind of idealized, but this will happen from negative infinity to plus infinity. Okay, and similarly, you have a discrete time periodic signal. It just also something that keep happening by itself. So we see this 1 minus 1, or actually probably minus half. Anyway, we made 2 minus 1. So you see this plus plus negative thing keep happening, and they also stretching from negative infinity to plus infinity. So that's periodic signal. Okay, and so that's the intuition about periodic signal, but we need a mathematical formulation for them. So the mathematical formulation of them is what we use, what we just write. Okay. So to describe the thing keep happening, we use this. We use the time shift that we just talking about. Okay. So we say the signal is keep repeating itself. If you shift by some number, that's called a period. If you shift to, I guess left and right doesn't matter, but we are shifting left right now. So if you shift the whole signal from negativity plus infinity by left by some number, and it actually becomes the same signal, then it's a periodic signal. So the idea here is you see those periods keep repeating. So if you shift by this period big T here, and then this part will become this part will coincide with this part, and this part will coincide with this part, etc. Right? And yeah, so if it keep repeating itself, then you shoot by one slot, and they will be the same repeating itself, and they will be the same signal. So this is a definition of periodic signal. Your signal x of t equal to x over t plus some big T. For some big T that's greater than 0, and yeah, and this is equal for all value of small t. So it's the same signal throughout this whole line. Okay. And similarly, you have the periodic signal for discrete time. You just change n to small n. Yeah, you just change t to n. So instead of big T, you have big N here. And you also want big N greater than 0, and the whole signal. So you should left by this big N, and the signal should look all the same. So you see that in this signal, if you shift to the left by 3 units, then it will look totally the same, because this point becomes this point, and this point becomes this point, this point becomes this point, and yeah, because it keeps repeating itself by this period of 3. So if you shift everything to the left by 3, it will be the same signal from left infinity to plus infinity. Okay, so that's the definition of periodic signal. Got any question? Yeah, it's a definition that you should remember. Okay. And let's talk more detail about this thing. Okay. And yeah, as we said, so this is what the mathematical definition of a periodic signal. You shift by some the period big T or big N, then the signal is unchanged. Okay. Oh, I guess we didn't say this is a period. But anyway, so this big T and big N are called the period for this periodic signal. Okay. And let me write it down so I can remember. So those two things are called the period. Wait, Control P, Control P. So those are called period. Period. Okay, and yeah, as we said, by definition, the periodic signal is unchanged if you time shift by big T and big N. Okay, and then we start have interesting. We see that we can also shift by other number. So if you shift by big T, it doesn't change. Then you shift by 2T, also doesn't change, because yeah, you shift by 2T, you shift by T doesn't change. Then you shift by T again, it still doesn't change. Okay, and yeah, you can kind of see. So if you shift this by 2T to here, then it also doesn't change. And yeah, so you choose basically you shift by any integer of T, the signal doesn't change. So you can have many different periods. So if x of t equals to x over t plus big T, then x of t also equals to x of t plus 2t, basically, or 3t or 4t, or any integer t. Okay? And similarly for discrete signal. Okay? So you see that this t and the big T and the big N here are not unique. So as long as you can find some big T and a big N, then it's called a periodic signal. But there is one of them. Usually there's one of them that's very special, and that's called the fundamental period. Okay. So the fundamental period is the smallest big T and big N that's positive, and yeah, That's small is big T and big bigger than positive, and make this equation satisfied. Okay, and they are usually denoted as T0 or N0. So that's the fundamental period, and this definition is very important. Okay, and there is a special case here that there is a function that's periodic, but the fundamental period is undefined. That are the constant functions. I guess that's more than one function. And we are talking about signal, so I should say constant signal. But anyway, we have a constant signal, then it's a bit funny. Because AVT, so your function is say x of t equal to 1. Then you see that you should by any big T here, then you still get the same function back. And so you cannot find the smallest big T that makes this thing the same. Okay, so it will equal to x of t plus big T for all big T, right? And so this thing you cannot find the fundamental period, but it's also periodic. Okay, so that's a bit funny. That's the constant signal. But anyway, for all other signals, you can find the smallest big T or big N, and that's a fundamental period. And the fundamental periods are very important because once you find the fundamental period, you can find all other period. So this is something you can prove in homework, that T is a period. So T can satisfy this if only if T equal to KT0. So and where K is a natural number. Okay. Okay. And if T0 is a fundamental period. So I guess if part is pretty easy. So if T0, because T0 is a period, then any constant times T0 will also make this equation satisfy. And you need to think a little bit about why all other T. So why if you have a T that's not integer multiple of this, then you cannot be not an integer multiple of fundamental period, then you cannot be a period of your signal. Okay, so that's something you can think about in your homework. And finally, it's just an N. So if you can find some T or N like this, then your signal is called periodic. And if you are not periodic, it's just called aperiodic. Okay. Any questions so far? We have quite a big concept. So we define the period, and we define fundamental period, and we say there are a lot of periods for a signal, actually infinite number of them, but they are all integer multiple of your fundamental period. Okay, and so let's see more example. So periodic signal. These two signals you should see them in high school is the sine function and the cosine function. And they are they are periodic because you can find this. So x of t equal to cosine of t, then x of t equal to x of question.
So if the signal is limited, so for example, t0 is the right limit, t1 is left limit. If the value bigger than the
Yeah. So
you know what I mean.
Yeah, I know what you mean. And
it's
not periodic.
Oh, okay.
Yeah. Yeah. So the question is that I guess I can draw here. The question is that if you have a signal, maybe if I use this, if your signal is like just these three things here, right? And then it doesn't extend to minus infinity to plus infinity, so it's 0 all the way outside. Then it doesn't satisfy this equation, right? Because if you shift to left by some number, then you will shift this block to the original empty block, and then it's not periodic. So for periodic signal, you need to extend to negative infinity and extend to plus infinity. Yeah, you need to keep repeating itself. Yeah. Okay. Then I guess I can erase this. Okay. Yeah. We'll see some phenomena related to this later. Because the periodic signal always extend to negative infinity and positive infinity, then usually they have infinite energy because they have some constant power and they extend to plus negative infinity, so the energy will be infinite. I guess there is a special case when it's just 0, but it's a really special case. Okay. Yeah. And let's go back to this a bit easier example. I guess now we draw this sine and cosine a little bit. So you have our cosine function. No, it's annoying. Okay, yeah, so cosine function, and from high school math, you know that cosine t equal to cosine t plus 2 pi. Then, yeah, so you see that 2 pi is the period of this cosine function, and the cosine is periodic. And similarly, if x of t equal to sine of t, then sine t equal to sine t plus 2 pi, and sine of t is also periodic. Let's just draw this. Sorry, indeterminate, but I guess let's draw one of them too. I will see a lot of them later. And where am I? Here. Wait, excuse me. Why is this not working? Okay, and yeah, so cosine function look like this. The cosine function is 1 to -1, right? And 2 plus 1, so keep going up and down, up and down. Okay, this is a very ugly cosine. But yeah, so it's 1 and -1, and I think this is pi, and this is 2 pi. Right? So cosine function keeps like this oscillation from -infinity to +infinity, and sine is like starting here. Yeah. Okay, so the sine function and the cosine function, and then we have an interesting example here now. So what if we try to combine cosine function and the sine function? Then is this periodic? So we have this function that's cosine if it's less than 0, and sine if it's greater or equal to 0. Then, yeah, I guess the answer is here. This is not periodic. But anyone want to answer why this is not periodic? So if you shift left and right, which part give it not periodic? Make it very hard to have a periodic. Okay. And what happened is this middle part. Okay. So this function, it looks very periodic on left and very periodic on right. But in this middle part, this is like a unique point here, right? So you get a discontinuity here, and you see that you cannot find this part on any other part of the signal. So if you shift this whole signal left and right, you can never match this on other place. So this is not a periodic signal. Okay. Yeah. So that's periodic signal. Very important. So let's see again. This is our definition. Yeah. So periodic signal is a key signal that keeps repeating itself from negative infinity to +infinity. And the definition, mathematical definition, is that go to another concept that's related to the change on our independent variable. So remember, we can make a negative sign. We can do time reversal on our signal. So there are two possible symmetry on when you do time reversal on your signal. So the first kind of symmetry is your function is even. That means that you do a time reversal on a signal, your signal just don't change. So usually look like this. Those are even functions. Basically, they look the same on the left part and the right part. And yeah, so when you do a time reversal, you flip them around, you flip back to the same signal. Okay, so those are even signals. And they are called even because they are basically, so if you write the Taylor expansion, they are polynomials of even power. So for example, x equal to t squared, it will be a even signal. Okay, so it's a signal of even power to t. Okay, yeah. So I guess the signal with even power with the polynomial even power to t will be even. Okay, And so that's even signal, and there are other things that can happen. So there are other signal that what happen is you flip it left and right. So add a minus sign to t, then this whole signal get the negative side. So when you flip left and right, then the signal actually get flipped up and down. Okay, so like this. So you flip it here, then you see this part is negative of this part. So yeah, so you flip left and right equal to flip up and down. So those are odd signal, and yeah, they are called odd because just like the even one, they are related to the polynomial of odd power. So like x to the t cube is odd signal. Okay, so those are even and odd signal. Okay. And well, even odd signal are nice because they have lots of symmetry, and we'll see later in course that the symmetry give them some nice properties. And also a nice thing we can do is we can actually decompose any signal to a sum of even part and odd part. I guess this is the first decomposition we're doing in this course. Okay? Of a signal into different parts, but this is the first one. So we can so what we mean is we can write our x of t to some even part of x of t plus the odd part of x of t. And this even part will be an even signal, and the odd part will be an odd signal. Okay. And even part of x of t is calculated as so it's the average of x of t and the time reverse of x of t. So you add together x of t and x of minus t, and this will be an even function because if you try to do a time reversal on this, the x over t becomes x over minus t, x over minus t becomes x over t. But addition is commutative, so x over t plus x over minus t equal to x over minus t plus x over t, so those are the same. And the odd part is similar, and the odd part is x over t minus x over minus t. And you see that if you try to do a time reversal on it, so you change x over t to x over minus t, x over minus t to x over t, then you pick out minus sign. So this is odd function. So we prove that this is an even function and this is odd function, and then you can also see that those two functions adding together give you back x over t. Because if you add this term with this term, then this x over minus t part just cancel out, and you get 1 over 2 x over t plus x over t just equal to x over t. Okay? Yeah. So this is a decomposition of a signal into odd part and even part. And let's see this in actual example. So you have whatever signal here. So this is the signal here that's 1 and 0, 1, 2, 3, and you can see that it's neither even nor odd because you go to x over minus n. So you flip it left and right around n equal to 0. Then x over minus n, look at this, is 1 and minus 3, minus 2, minus 1, minus 0. Oh, sorry, minus 1 and 0. Okay, so x over n look like this, x over minus n look like this. Then the even part is this plus this divided by 2. So you will get a whole bunch of 1/2. So at minus 3, minus 2, minus 1, and plus 1, plus 2, plus 3, you get 1/2. And in the middle part, 0 part, you get 1 plus 1 divided by 2, you get 1. Okay. So this is even one, and so this plus this divided by 2, you see is the even function. And similarly, you have x over n minus x over minus n divided by 2, then you see you get the odd function. So at n equals 0, you have 1 minus 1 becomes 0. And then the other part, you have the 1/2 x over n, you have 1/2 here, and minus 1/2 x over minus n, you get this minus 1/2 here. Okay. So this is even odd decomposition of a signal. Okay. Any question? This is rather simple. Okay. No question. We are in funny time. I guess we can keep going. Okay. So let's keep going because we have quite a bit of schedule. Okay, so that's 1.2, and let's go to 1.3. So 1.3 we'll talk about exponential signals, and but for now, for 5 minutes, let's do other thing first. So the first thing we do is a review of complex number. Okay, hopefully everyone is in high school or calculus. Okay. But anyway, complex number are number that has a real part and a imaginary part. Okay, so usually they are written as so for the real and imaginary part representation, we can write z equals sigma plus j omega, where j is the complex number symbol. So j equal to square root of -1. Okay, so we have some notation here. Yeah, because we are kind of an engineering course, so the complex number symbol we don't use I. I guess I is for current. Okay, so we use j for square root of -1. And well, complex number has real part and imaginary part, so it's sigma plus j omega. And here we can also express the complex number in this complex plane. So it has two coordinates, sigma and omega. So the real part is sigma and the imaginary part is omega. Okay, and a very interesting thing about complex number is you can change between the polar coordinate and the Cartesian coordinate. So in the Cartesian coordinate, I mean you write this complex number as a real part and imaginary part. But you can also express this point. So this point z is represent our complex number z. You can also represent this point as a polar coordinate, meaning that you can write the distance of it to the original, so this r, and this theta to the x-axis. Okay, so you can change back forth between sigma omega and r theta. Okay. And so we have the first change here. I guess then we have okay, so it's a bit funny. So here we have how to change from polar coordinate to the Cartesian coordinate here. So this is really just geometry. So you have r here and the theta here. Then sigma is r cosine theta by the trigonometry, because this is orthogonal triangle here. Excuse me. So r cosine theta equal to sigma, and r sine theta will equal to omega. So that's how you change from r and theta to sigma and omega. And you can also do another way around with trigonometry. So if you have the sigma and the omega, then you can you can calculate r and theta by, so r equal to square root of sigma squared from omega squared just by Pythagorean theorem. And then you can calculate theta by different ways, but one of them is you can say tangent theta is omega divided by sigma. Okay. So that's some geometry here, and now we see something actually interesting. Okay. So in calculus, you should learn this Euler's relation. Okay, and this relation let us express the complex number in polar coordinate really nicely. Okay, so Euler's relation says that e to the j theta equal to cosine theta plus j sine theta for every theta. And remember, this j is the complex number j, and the e is the natural log e. Okay. So if e to the j theta equals to cosine theta plus j sine theta, then our complex number as sigma plus j omega will equal to r cosine theta plus j sine theta. This is just from the trigonometry we calculated already here. So sigma equal to r cosine theta and omega equal to r sine theta. J sine theta. Omega equal to r sine theta. Okay, and so we take out r here, then we have r and cosine theta plus j sine theta. Then by this Euler relationship, we see that z equal to r times e to the j theta. Okay, so we see that in polar coordinate we can also express z in this nice expression. So this complex number here, z here with the real part sigma and the imaginary part omega. Then, and also polar coordinate is radius r and the angle theta. So this z will be r times e to the j theta. Okay, so this is important. Okay, and so that's very cool. This is a very cool way to express your complex number. We'll express our complex number in Cartesian coordinate or polar coordinate depending on our need. Okay, and also we'll I guess 1 minute. Yeah, and yeah. So another back and forth thing we'll keep doing is, I guess it's kind of like a change between polar and the Cartesian coordinate. Is we'll use Euler relationship to change from this e to a j theta to cosine theta and j sine theta, or we can have this reverse Euler relationship that express cosine theta as a linear combination of e to a j theta and e to a minus j theta, and the sine theta as a linear combination of e to a j theta and e to a minus j theta. And yeah, we'll talk about the derivation in next class. Okay, so yeah, let's have a 10-minute break.美术才不会上课。
那作业要怎么交？
作业 online 交，或者是丢到助教办公室。助教，我看一下，我们办公室应该有合适可以丢吗？
对，
对。我写一下好了。算了。什么东西？
做礼拜三。下礼拜是放。
没有，没在礼拜五放假。没有，就是其他比较大的运动会之类的。
请问作业什么时候发网络上？
作业等一下，今天会发。
它是会放到哪里？作业测验还是公告？
应该是，应该是档案之类的吧，可能应该会在 CH1 下面之类的。
所以就可能我会在 CH1
对啊，可能在 CH1 那里，对。对。Hello. Okay. Any questions so far? No. Okay, let's get back. So Euler's relationship. Okay, so Euler's relationship, we can think of it like changing from the polar coordinate of a complex number to the Cartesian coordinate. So if you use Euler relationship, then you can change a complex number in terms of I e to I theta to the sigma plus j omega, and you know that sigma equal to r cosine theta and omega equal to j sin theta, because you break it is e to a j theta to cosine theta plus j sin theta. And one thing we'll do is sometimes in these courses we do this we call what I call reverse Euler's relationship. That is, you want to express a cosine theta or sin theta in terms of complex exponentials. So this is e to a j theta. And how you do this is you also know that you can have e to the minus theta equal to cosine theta minus j sin theta. And so if you add those two equations together and divide by 2, you see that cosine theta equal to e to a j theta plus e to a minus j theta divided by 2. And if you subtract those two equations, then you see that the sin theta, so you have e to a j theta minus e to a minus j theta equal to 2j times sin theta. So you have sin theta equal to e to a j theta minus e to a minus j theta divided by 2j. So those two relationships are actually useful because you want to express cosine theta and sin theta instead of j theta and e to a minus j theta. Okay. No question, then let's actually go to section 3.1. So we are going to talk about tangential time complex exponential and sinusoidal sine function, sinusoidal signals. Okay. And so what are continuous time complex exponential? Well, the complex exponential signal, well, in a very general form, they are signal with this form. So it's a complex exponential. So it's exponential to some complex number a and time t, and you can also have some amplitude c here. So in very general form, c is some complex number and a is also a complex number. And okay, and we'll see later why, but we would like to express the a in Cartesian coordinate and the c in polar coordinate. And so give some idea. For a very special case, if C and A are both real, then we have a kind of exponential signal expected. Okay, so A bigger than 0, then you have a growing exponential. A less than 0, you have a decaying exponential. But we will actually not use those signals. It's just something here for you to see. Yeah, later part of the course we don't really use that. The C we actually use are those periodic complex exponential because, well, it's periodic. We want to talk about periodic function a lot. Okay, so periodic complex exponential and sinusoidal functions. Okay, and what are periodic complex exponential? The complex exponential can be periodic. It happens when your A is purely imaginary. So remember, that's kind of why we want to restrict it. Write A in terms of sigma plus j omega. Okay. So if A is purely imaginary, then your signal is C times e to the j some omega naught 0. Okay. So let's write this omega in terms of omega naught for a reason we'll see. Okay. So x of t equal to C times j e to the j omega naught t. Okay. So this is just our complex exponential with A being purely imaginary. So we have this j here, and omega naught is real now. Okay. And this is actually periodic for any omega naught and c. Okay. And we can find its period by, well, solving our periodic equation. Okay. So remember our periodic equation says x of t should equal to x of t plus big T. So x of t equal to this thing, just because it writes this. And x of t plus big T is basically the same thing, but t plus big T here. Okay, small t plus big T. And we can try to solve this equation. And here we assume c not equals 0 to make things a bit easier. So because c equals 0, this is a trivial signal. Okay, so c not equals 0, so we cancel c here. And then we try to solve this, and you see that, well, this is true for every t, so we can assume t kind of not equal 0, small t not equal 0. So we also cancel out this e to a j omega t one side on this side and e to a j omega t on this side. Then we left with e to a j omega big T equal to 1. and this is the important equation, kind of important equation. So we see that if you want a big T to a period, then e to the j omega naught big T need to equal to 1. Okay. And we can analyze this for different case. So for omega, so another singular case. So if omega naught equal to 0, then this thing is always 0. So it is always e to the 1. Okay. So your x to t will become c. Yeah. So yeah, omega naught equals 0, then your x function actually becomes a constant function because the t get multiplied by 0. Okay. So your x of t equals to 1, and you got this constant signal here, and so it's periodic for any value of big T. But there is no fundamental period, as we said. And on the other hand, so if you have a more conventional signal, so omega not equal to 0, then we can find the fundamental period T naught. That's the smallest big T that satisfies this equation. And that happens actually when T naught equal to 2 pi divided by absolute value of omega naught. Because this thing equal to 1 only when this omega naught T is a multiple of 2 pi. Because we know e to the 2 pi j equal to 1. And that's also related to the picture here. So our complex number is something like this. So if you want this complex number equal to 1, then you want its radius to equal to 1, and this theta is a multiple of 2 pi, right? Because if you see this r e to the j theta of your complex number, then when theta not equal to 0, then you are in somewhere in a complex number plane, and you cannot be this 1. Okay. So your theta need to be multiple of 2 pi, and r need to equal to 1. Well, r is already equal to 1, and you want the theta part to equal to multiple of 2 pi. And yeah, and the smallest possible t, and which is also positive for this to satisfy is just 2 pi divided by absolute value of omega naught. And also because you have absolute value here, then you see that e to the j omega t and e to the minus j omega t has the same fundamental period. So remember, we have fundamental period bigger than 0. Okay. And yeah, that's why I have the absolute value sign here. Yeah. One thing remember, fundamental period is always bigger than 0, and so you have absolute, but omega naught can be negative, so you have absolute value sign on omega naught here, and e to the j omega naught t and e to the minus j omega naught t has the same fundamental period. Okay. So yeah, so this is a signal we will look through the whole class. We will see them a lot. It's a complex exponential e to the j omega t times on c. So any questions so far? And they are very nice. You can calculate or basically just read the fundamental period from here. The fundamental period is 2 pi divided by absolute value of omega naught. Omega naught is this omega naught just in this equation. Okay, yeah, periodic, and we know it's fundamental period. Any question? Okay, if not, then let's go to a bit of boring part. So this is where why we talk about Euler relationship and Euler with Euler. That is, now we want to write those sine and cosine function. Okay. So signal really related to the periodic complex exponential. Those e to the j omega naught t that we're just talking about is this cosine and sine function. So x of t equal to a cosine omega t plus phi. Okay. And yeah. And here we talk about some convention first. So here the convention, so this omega naught convention is like what do we have? Is in radian. So omega naught t equal to 2 pi, it goes back is 1 period. And sometimes you also want to write your frequency in terms of how many cycles per second, so hertz. And that's the frequency will be like omega naught divided by 2 pi. So yeah, so omega naught is 2 pi times this cycle per second frequency. Okay. And anyway, so this thing also has the same fundamental period, similar fundamental period of 2 pi divided by omega naught absolute value. You can just verify this easily. And the signal will look like this. It has amplitude A, and is shifted by some phi here. So I guess it shift to right it doesn't really matter because it's periodic. So it should be by some phi, and it has some t naught equal to 2 pi divided by omega naught. Okay, and you see that this point is a cosine phi. Okay. Yeah, and okay, and something funny here is in this expression here, we assume omega naught and phi are real. Okay, so that's just like the omega naught here is real. If omega naught here is not real, then it's not periodic. Okay, so similarly, I guess phi, okay, it's a bit complicated, but anyway, omega naught and phi is real, but A can be complex. So that's some subtle point. Okay, so this is our continuous time sinusoidal signal. It's also periodic, and because it's usually if A is real, it's a real function, so we can plot it. Okay, and now let's go to the Euler relationship. So we can now change back and forth between periodic complex exponential and the sinusoidal signal. Okay, so first we can write our periodic complex exponential as the linear combination of sinusoidal signal. So it's just very direct breakdown of this e to the j omega t. So e to the j omega t equal to cosine omega t plus j sine omega t. So this thing is just c cosine omega t plus j c sine omega t. So see, you can write complex exponential in terms of sinusoidal. And similarly, you can also write the sinusoidal as a linear combination of periodic complex exponential. So this is where we use our reverse Euler's relationship. So your cosine omega naught t plus phi is e to the j omega t plus phi e to the j omega t plus phi divided by 2, and e to the minus j omega t plus phi divided by 2. And you can kind of write it in this way. So you can take out, okay, and yeah. So this theta is omega t plus phi, and you can do some arithmetic to single out the j omega t part and e to the minus j omega t part, and kind of combine the j phi part with A and the e to the minus j phi part with A. And but anyway, so you see this is some coefficient times your e to the j omega naught t, and another coefficient times e to the minus j omega naught t. So you can see that you can change back and forth between this sine cosine and e to the j omega, e to the minus j omega. Okay, and another way to express your sinusoidal in terms of complex exponential is you say a cosine omega t plus phi is just a real part of e to the j omega t plus phi. Okay. And yeah, and similarly you can say the sine omega t plus phi is the imaginary part of e to the j omega t plus phi. And here we introduce some notation, and the font is a bit funny, so sometimes it looks not so nice. But anyway, so we write this RE as taking a real part, and IM as taking an imaginary part, and hopefully they are readable. Yeah, throughout the lecture note. Okay, so it's taking a real part, taking an imaginary part. Okay, question. Changing back forth between complex exponential and the sinusoidal signal. Okay, if not, okay, then let's introduce another concept. So we have fundamental period of any signal, and but for this continuous time. So for the continuous time sinusoidal signal and the periodic complex exponential, we can excuse me. We can define this. We see that this omega naught is very important, so we can define its absolute value of omega naught as the fundamental frequency. Okay, and anyway, so this is the equation we had before. So remember, we say the fundamental period is 2 pi divided by this absolute value of omega naught. And now we call the absolute value of omega naught as the fundamental frequency. Okay, and okay, so here's okay, and it's a bit confusing here, but remember we are not actually have a circular logic. So logic here should go like this. So I have a reverse order here. So remember, fundamental period is a well-defined concept for any signal. So fundamental period is the smallest possible period, and so logic goes like you calculate smallest possible period is the fundamental period. Then from fundamental period, you can calculate the fundamental frequency by having fundamental frequency equal to 2 pi divided by fundamental period. Okay. So that's how we define fundamental frequency. Okay. And we see that fundamental frequency is a nice concept because we kind of just appear in the equation everywhere when we write the complex exponential and the sinusoidal signal. So it's an absolute sign. So for complex exponential and the sinusoidal signal, the fundamental period is just absolute value of this omega naught. So this omega naught here, this omega naught here, and this omega naught here is the fundamental frequency. And so for continuous time signal, fundamental frequency and the fundamental period are related nicely. Okay, so yeah, so it's just one is another dividing 2 pi. Okay. Fundamental period is 2 pi divided by fundamental frequency. Fundamental frequency is 2 pi divided by fundamental period. Although the fundamental period is where, if you want to go by definition, this is what starting the definition chain. Okay. And we can visualize the frequency quite nicely in this picture. So you see the frequency has quite an intuitive meaning. If your frequency is higher, then your signal will oscillate faster. So here are a whole bunch of cosine signal with higher frequency. So we have omega 1 bigger than omega 2 and bigger than omega 3, and you see the oscillation getting faster and faster, and which also means that the period getting larger and larger. Frequency getting slower and slower from 1 to 3. And that means the period getting larger and larger. Okay. So this is the highest frequency, this is the lowest frequency, and you see the period getting larger, larger, larger. Okay. So that's the idea about fundamental frequency. Okay. And then is next one. Oh, okay, the question about fundamental frequency. So it's from the equation, it's really easy. Yeah. It's just omega naught taking the absolute value, but the definition is 2 pi divided by fundamental period. Okay, I have no question. Then let's go to another concept. This is, it's not quite a concept, but something we talk about. So, interesting about this complex exponential and the sinusoidal signal is that they have usually, most of the time, they have this finite average power. And that means that they have infinite total energy. And you can see that so remember, instantaneous power is the absolute value squared. So I guess it's easier to see in complex exponential. So for complex exponential, the absolute value here is 1 and 1 squared is 1. So the power is just 1 if c equals to 1. Okay? And so power is always 1. So the energy you spend is just whatever time you have, and power is always 1, and the average power is always 1, and so average power is always 1, but if you take the energy to infinity, then if you take the period to infinity, then the energy will be infinite. Okay, so that's the energy power for periodic complex exponential. And the sinusoidal signal is a little more complicated, but they also have constant average power usually, in some sense. Okay. Anyway, yeah. But I guess this is true for both the complex exponential and the sinusoidal signal. That is, their infinite average power is the average power over infinite time is always a constant. Okay, then no question. Then let's go to a very important concept now. Yeah, this is also something we are going to see throughout the whole class. That's the harmonically related complex exponential. Yeah. And so what are those harmonic related complex exponential? there are complex exponential that have the same period. Okay, that sounds a bit weird because we just say that the period and the frequency are kind of related by 2 pi, right? We keep talking about fundamental period of a complex exponential. So let's say a complex exponential of this from e to a j omega t. We say the fundamental frequency and the fundamental period are just related by like multiplying together into 2 pi. So higher omega will give you smaller fundamental period. But you can still have different omega giving you by having same period by something like this. Okay, so if you fix some period t naught here, and so here is something that you think so. Here is a signal. Okay, we didn't write the infinite part, so you imagine this continue to plus and minus infinity. Okay, so here is a signal that so we fix on t naught here, and here is a signal that has fundamental period t naught. It sounds like well, it's very sinusoidal, but imagine this is a complex exponential and just real part. Okay, so here is a signal that has a fundamental period t naught. And yeah, but so you kind of think that omega is fixed this way, but you can also have t naught being twice the period of this e to a j omega t. Okay, so this is also another signal that has a period equal to t naught. So its fundamental period is t naught divided by 2, but t naught is also a signal, is also a period of this signal, right? And you can keep going. You can have higher and higher frequency, and having the t naught as the integer multiple of the fundamental period of the signal. Okay. Okay. So those are the set of harmonic related signals. So they have a common period t naught, and but they have a different omega here. Okay. You can have higher and higher omega, and keep having t naught as a layer period. And so let's solve this equation. Okay. So you want t naught to be a period of your signal. And what you solve is e to a j omega t naught. Then it's necessary that e to a j omega t naught equal to 1 because e to a j omega t naught should equal to e to a j omega 0 equal to 1. Okay. And yeah, and so this means that omega t naught is multiple of 2 pi, just like our analysis of the complex number before. Okay. So omega t naught equal to 2 pi times the integer k. Equals 0 plus minus 1 plus minus 2. Okay, and now we define some number. We define omega naught as 2 pi divided by t naught. Then we see that omega equal to omega naught times k. So omega naught will basically be omega of this one. Okay. This is omega naught is when t naught is the fundamental period. So omega naught is 2 pi divided by t naught. And then you see that all those higher order harmonic, they have their frequency equal to integer times 0 omega naught. Something funny is you can actually also have the negative integer, but yeah, you have this harmonics of your period t naught. Okay. Okay. So those are the okay. So we say this is a necessary condition, but and you can easily check that this is also sufficient. So if omega equal to omega naught, so I guess here you can. I guess it's not quite in homework. You can just check yourself when you have extra time. So you can check. You can check that this is sufficient. Check. Sufficient. This is sufficient for the signal to be periodic with period t naught. Okay, and yeah, so those are the periodic. So those are what we call harmonic related complex exponential. I guess we kind of assume c equals to 1 here. Okay, so we talk about harmonic related complex exponential. We have c equal to 1 and later we have a linear combination of them. But anyway, harmonic related complex exponential is a set of periodic exponential with a fundamental frequency that are multiple of this omega naught. So those harmonic related complex exponential, we call them phi k. Phi k of t equal to e to a j k omega naught t. Okay, the important thing here is the k. So k is a multiplier here, and it's an integer. Okay. So this k is important, and k is an integer, 0 plus minus 1 plus minus 2. Okay. And so for example, k equals 2 here, and k equals 3 here. And you can also imagine there's a funny thing when k equals 0. So k equals 0 is actually a constant function. So the constant function is also a harmonic exponential because, well, every period is a period of the constant function. Okay, and later we'll see that harmonic related complex exponential are very important because you can basically build any periodic signal with period t0 from those things. Okay, so you can write any signal, well, a nice signal with period t0 as a linear combination of those harmonic related complex exponential associated with t0. Okay, and here's what we say. So for k equals 0, your phi k is a constant function because well, this is just 1. Okay, and so that's a special case. But for other k, your phi k of t is periodic with the fundamental frequency k omega naught. So absolute k omega naught, and the fundamental period is t naught divided by your absolute value of k. Okay, and yeah. Any question on this harmonic related complex exponential? I guess let's go back again to see the intuition. So here we have k equal to 2, k equal to 3, and you see that the frequency is the frequency here is twice omega naught, and the frequency is 3 times omega naught, and the period is t naught divided by 2, and the period here is t naught divided by 3. Okay. So just like what we see here. Okay. And yeah, that's the example of signal and periodic signal, and want to calculate its fundamental period. Okay. And so in this example, we have a signal that's a linear combination of two periodic complex exponential, but with different omega. So first one has omega equal to 2, and the second one has omega equal to 3. And then we can first calculate the fundamental period. So we know fundamental period is 2 pi divided by omega. So 2 pi divided by this is pi, and 2 pi divided by this is 2 pi divided by 3. And so if we want to find the fundamental period of this whole signal, then we want it to be a multiple of both the first part of a signal and the second part of a signal. Okay. And yeah, so we want the smallest possible multiple of both of these. Then you see that is actually 2 pi. So 2 pi is 2 times this pi, and 3 times this 2 pi divided by 3. And so the fundamental period of this signal is 2 pi. Okay, question. So yeah, so this is also a kind of question you will see in your homework. So we'll give you a whatever signal, and we'll ask what's the fundamental period. Okay, and you need to do some derivation sometimes. Okay, and also for this signal, we can try to express it in a nicer way in terms of sine and cosine. Okay, so how do we express it in terms of sine and cosine? I guess in terms of cosine is, remember cosine equal to some e to the j theta plus e to the minus j theta. So we try to match the plus j theta and the minus j theta here. So we take out a vector that's the middle of these 2 and 3. So we took out the e to the j 2.5t, and then we are left with e to the j 0.5t and the e to the minus j plus 0.5t. And so this part looks like the cosine. This is twice cosine 0.5t. And then we have another complex part. Another complex exponential part, e to the j 2.5t. Okay, and Yeah. But then if we take the magnitude of this whole thing, then we see that this e to the j 2.5t has a magnitude 1. And the magnitude of this is just the magnitude of cosine 0.5t, and so it will look like this. Okay, so here is some mathematical manipulation you can use to see a little better about this signal. So this signal is kind of like a cosine part, and but with this complex oscillating, complex rotating amplitude. Okay, that's okay-ish example. Okay, the next part, which is basically just a little showing. So we back to more general complex exponential, which is not as important as our periodic complex exponential, but we'll see some picture. So more general complex exponential, we have the C and the A, all complex number. And as we said, we want to write C in polar form and A in rectangular form. And we can just do math. So C in polar form is absolute value C times e to the j theta. Then A in rectangular form, so e to the r plus j omega naught t. And then we do arithmetic. So e to the rt we took pick out, and so basically we want to group together the real part of e to the something and the imaginary part of e to the something. So imaginary part of e to the something, you have is e to the j theta and e to the j omega naught t. So here we already have the c and the e to the rt. These are all real, so this is just some real signal here. So real exponential signal here. So we have e to the rt times is cosine omega naught t plus theta, or the imaginary part is c to the rt, c times e to the rt, then sine omega naught t plus theta. So we see that the real part and imaginary part are just growing or decaying sinusoidal signal. So for example, the real part is this thing. So it's like this. Okay. So C to the RT. So when R equals 0 is some growing exponential here, then you have the cosine omega t plus theta oscillating inside this envelope. And if R is less than 0, then you have this decaying exponential amplitude, and you have this cosine oscillating inside. Okay, so yeah, those are nice picture. Okay, any question? Oh yeah, please.
Example 1.5.
1.5, sure.
So why we want to use 0.5, not 1 or 2, or?
You want to use 0.5. Because you want these two to match, right? You want this plus 0.5 and then minus negative 0.5 here.
How about 1 or 1?
What do you mean 1?
I mean, 1 is j t plus exponential j 1t.
So you want e to the
0.5 with 1, the number 1.
number 1. Wait, say again?
为什么一定要用0.5而不是用1，然后不是用其他数字？
因为2跟3的差距是1啊，所以2在这里，然后3在这里，然后你要取中间，然后这差距是0.5嘛，对吧？I guess for example， 对吧？
因为这个东西它是cosine。
嗯哼，对，因为 cosine theta 是大概是 e to the j theta 加上 e to the minus j theta 嘛，所以你希望这里这个 theta 跟这里这个 theta 是一样的，所以希望这里是负0.5，这里正0.5。所以例如说你这里拿个随便吧 ，e to the j2t 的出来的话，那也是1加上 e to the jt， 对吧？那这个是没有配起来的，那也没办法把它变成 cosine。OK。OK， is that OK？ 哦，question。
我想问一下，就是下面那个，就是你1的2.5JT 就放不见。
哦，那只是因为我们取了绝对值啊，取了绝对值的话，这绝对是1这样子。原1，对啊 ，e to 的 j omega t for any omega 是等于1的嘛？
哦。
对，这只是取绝对值而已。对，这个其实是个。对吧？这个是其实有个 目标有点随性的，但是总之我们就是算出了个它的绝对值长这样子。对。Okay. Any other question? Okay. If not, then let's go to next part. I think we are short on time, but anyway, we'll try to see what we can do. I guess it's okay. So let's see the discrete time complex exponential. Okay, so discrete time complex exponential and the sinusoidal. They are a bit similar to the continuous time, but we are going to see different part. Okay, so discrete time. So one thing we'll do a lot about discrete signal is we'll do this thing. So in continuous time we say is c to the at, and with continuous time we have c to the beta n. So for now it's similar, but what we'll do is we'll define alpha equal to this e to the beta. Okay. Yeah, we'll see why this is useful. Okay. So we say e to the beta equals some alpha, and our x of n is c times alpha to the n. Okay. Okay. So for now it's just change of a variable. Nothing really changed. So t to n. Okay. So c and alpha. Okay. But for now, then next we can see something interesting happen. So we can have alpha real, right? So both c and alpha real. And you see that we can have negative alpha, and this is some signal that you don't quite see in the continuous time. Okay. So in discrete time, you can have alpha positive and alpha negative. So alpha positive, then depending on whether alpha bigger than 1 or less than 1, you have this growing exponential or decaying exponential. But you can also have alpha negative, which actually correspond to like this a being complex number, but because you only take point in integer value, so you can have alpha negative, and you still have a totally real signal here. Okay, so you can have this alpha negative for your discrete time signal, and you see it's a very funny signal that oscillating up and down, up and down, up and down. Because at every time step you are multiplying real and negative alpha, so you get flip up and down, up and down, up and down. Okay, and then if the absolute value of alpha is less than 1, you still following kind of a decaying exponential. And if the absolute value of alpha is less than 1, is bigger than 1, then you have the growing exponential, which means alpha is less than minus 1. Okay. So yeah, so this up down thing you don't really see in continuous time. Only happen when you have discrete time. Okay. And yeah, so this is kind of why let you see why having this alpha here is nice for discrete time signal. Okay. And then the more important one is as usual, is the periodic complex exponential. So that's happen when beta is purely imaginary, and so yeah, the periodic complex exponential happen for continuous time when beta is purely imaginary, and it's similar for discrete time. And if beta is purely imaginary, that means that, but we want to express in alpha, and that means alpha has an absolute value equal to 1. Okay. And yeah. So alpha equal absolute value equal to 1. But for now, we kind of go back and forth. I guess for reasons we go back to this e to the j omega naught, and yeah, because we'll also, so we like this alpha notation, but so for discrete time it's complicated. We like this alpha to n notation, but sometimes we also like this e to the j omega naught n notation. Okay, so we kind of go back and forth. We just need to get used to it. And for now, let's try to analyze the signal in this e to the j omega naught n notation. Okay, so we want this periodic signal, and it's from e to the j omega naught n. Okay, and And we'll see very soon that something funny is that you can have a different beta giving you same alpha. Okay. I guess that's later. But anyway, so x equal to x of n equals c to j omega naught n, and yeah, and then you can also change it a little bit. So you can, if you think about c is complex, then you can write x of n equals a e to j omega n plus 5. And then you can take the real part to get the cosine function and the imaginary part to get the sine function. So here the sine and cosine transformation is similar, so let's ignore that for now. Okay. Yeah. So I guess we okay. So sorry. So this is a discrete complex exponential with purely imaginary coefficient. So one thing to be careful now is that this is not necessarily periodic. So for continuous time, we just say signal with this form, we call it periodic. But for now, this is just a purely imaginary complex exponential, and we'll see what is periodic later. Hopefully today. And anyway, so you can do the sine and the cosine and e to the j omega and e to minus j omega n transformation similarly. So let's skip that. And for now, let's see some example of the complex of the function. So you have those. Okay. So some example of the discrete sinusoidal function, and so you have a cosine 2 pi n divided by 12 like this. Cosine 4 times 2 pi divided by 31 n, and cosine n divided by 6. So you can kind of feel a sinusoidal envelope outside, and but things are taking on those discrete points. Okay. And wait. Okay. We keep talking about. Okay. And then also have the general case. And this is not very important, so let's skip this very fast. So general case is similar to the continuous time. So you take the c in polar coordinate and I guess it's similar but not quite. But anyway, you can take c in polar coordinate and alpha also in polar coordinate, and you write your x of n as the cosine part, real part as a cosine function, and imaginary part as a sine function. Then you have as a growing or decaying sinusoidal function. So like this. So you have this c alpha to the n. And if alpha is bigger than 1, you have this growing exponential envelope. Alpha less than 1, you have this decaying exponential envelope. And you have this cosine omega t n plus theta oscillating inside, and things are taking on integer point. Okay. And we have 5 minutes. Can I talk a little about this? Let's try a little bit. Okay, but any questions so far? Okay. Yeah, we are a bit slow. I guess it's okay. Any questions so far? If not, then let's talk about in last 5 minutes the important thing. Okay, the important thing is when is our discrete time complex exponential being periodic? Okay. I guess let's try to. I guess we cannot really finish this part, but let's try to talk a little about it, and then we'll continue next time. Okay. And so continuous time complex exponential, as we say, is always periodic. It's very nice. You write this e to the j omega t, and it's periodic, and there is a period 2 pi divided by omega if omega is not 0. And but for discrete signal, it's very weird. Okay, so the first weird thing we see here is that this omega is kind of periodic in itself. So if you think about you change omega from some omega naught to omega naught plus 2 pi, then you see your signal become e to a j omega naught plus 2 pi n, and that's e to a j 2 pi n times e to a e j omega naught n. And by e to a j 2 pi n is just 1 always, because e to a j 2 pi equal to 1, and n is an integer, right? we always take a sample point at the integer point. Okay, so e to a j 2 pi n is always 1. So this is just e to a j omega naught n. Okay, and so yeah, so this is an important thing to remember throughout the whole course. That is the omega in discrete time signal. If you change it by a multiple of 2 pi, your signal don't actually change. Okay, and that means that you only need to keep track of your frequency in interval of 2 pi, and we can have different convention we use. Sometimes you use from 0 to 2 pi, sometimes you use from minus pi to pi. And low frequency signal will be signal with omega naught around multiple of 2 pi, so like a 0 or plus minus 2 pi, plus minus 4 pi, etc. And high frequency will be signal with plus minus pi with like odd multiple of pi, so like plus minus pi, and this plus minus 3 pi, etc. And do we have okay? And yeah, so high frequency means that the signal keep flipping up and down, up and down. So high frequency signal will look kind of, so like the highest frequency signal is e to the j pi n, right? So this is a low frequency signal, so omega naught equals to around 0, so your signal is just like constant. And the high frequency signal is e to the j pi n, and that is minus 1 to the n, so your signal can keep flipping up and down, and that's the highest frequency possible. And okay, so that's actually so for when is the signal periodic. So you have our signal is e to the j omega naught n, and as we say, continuous time this is also always periodic. But for discrete time signal, e to the j omega naught n is not always periodic. For this to be periodic, we need to you need to have some period n. So you need to have e to the j omega n plus some big N equal to j e to the j omega n. Okay. For n. And so you cancel the small n part out, then you get e to the j omega naught n equal to big N equal to 1. So big N is an integer because you only take integer points here. Okay, so that means omega naught n is a multiple of 2 pi, is also an integer multiple of 2 pi as usual. So you have omega naught n equal to 2 pi times another integer n. Okay. And so if you move things around, then that means omega naught divided by 2 pi equal to m divided by n, m divided by big N. But remember, so m is an integer like we say here, and but n is also an integer like we say, because this period must be an integer, right? Because it's a discrete signal, this big N must be an integer, and m is an integer like before. And yeah, and so you see omega naught is omega naught divided by 2 pi is integer divided by integer, so this is a rational number. So you see that your signal is periodic only when omega naught divided by 2 pi is a rational number. Okay. So this is very different from continuous time signal where you take whatever omega naught is periodic. You need to have very specific omega naught for your signal to be periodic. Okay. And yeah, and so this is a relationship for your signal to be a periodic signal, and then you can find the fundamental period here. So fundamental period is the smallest n that satisfies this equation. So if you are, so here is a bit confusing, but if you have some omega naught here, then the fundamental period n here is you can solve for smallest possible n that satisfies this equation, where m is also integer. So yeah, so n is the smallest number satisfying this equation. So you want to find the smallest possible m here. And yeah, and then the fundamental frequency is actually not omega naught. Fundamental frequency is omega naught divided by n. Okay. Yeah, because the fundamental frequency is 2 pi divided by n, and you solve the equation is omega naught divided by n. And we have more picture, but we're also out of time and it's Friday, so let's cut here. And yeah, let's see you on Tuesday.我们教OK，所以我们来看一下作业。